Today I would like to talk again about a dimensioning tool that finds digital filter coefficients for you. I made some improvements with cool features. In an earlier video I briefly explained how a digital filter works and how it can be dimensioned. Even when the principle is simple, it is unfortunately not so easy to determine the right filter coefficients. Therefore, I have provided a small Excel tool in the download area. You can use it to determine these filter coefficients. In the Excel sheet, you simply change the pitch value until the filter does exactly what you want to see. I'm doing this with a step function, but it could be any signal in the time domain and you always get the filter response on it. The tool provides you with the filter coefficients and you can simply use them in your code. I will explain later how exactly to do it. Yes, it might be really worth subscribing to the channel. I also link you to the video in the upper right corner. I think tinkering with electronics is more fun if you can play through these things virtually with that small tool. It also helps to better understand how digital filters work. Now I have thought about a few improvements for the Excel tool. I would like to be able to set both the resonance frequency and the damping separately on my filter. Yes, I had to think a bit about the realization, but I made it. Here are now two parameters which can adjust the resonance frequency and the damping of the filter separately. I have also implemented this principle as Arduino code, which I will present to you in a later video related to a nice project. Now I want to show what the filter's step response looks like when we change the resonant frequency from very low to very high. If the resonant frequency is lower than the fundamental frequency of our signal, then it will of course be severely damped. We see that here in our graph. If the resonant frequency of the filter is equal to the fundamental frequency of the signal, then we get the full amplitude and we see a resonant oscillation in the filter response. The filter even oscillates a bit further. It reminds me of a pendulum where you can change the pendulum frequency. If we keep increasing the resonant frequency, we get more and more overshoots after each step in the signal. But it is interesting that the filter response can now follow the signal steps much quicker. In physical terms, this means that the filter delay is reduced. Of course, this is of particularly interest when you need short delay. In some applications, you want exactly these overshoots. I will show you an interesting project in a later video. In most cases, however, one would like to avoid them as far as possible. And that's exactly what we are trying to do now. Next, we keep the resonant frequency constant and change the damping. If we increase the damping, then the oscillations decay faster. And at a certain point, even the overshoots disappear completely. We can find a compromise for the fastest possible transient with slight overshoots. I could play around with it for hours. This is also reminiscent of a mechanical pendulum that is dampened by air or a liquid, for example. If we reduce the damping, then it takes correspondingly longer for the oscillations to decay. In the extreme case, the filter even becomes unstable. That means it oscillates by itself. Okay, I gave you a simple Excel tool to approach digital filters in a playful way, without having to deal with filter theories and theorems of communications engineering. The exercise might help to discover your interest in it. If not, then that's okay too. You don't have to understand every theory 100% if you just want to make some practical applications. Here I have prepared another sheet for sophisticated makers. The filter coefficients shall be optimized in the presence of large noise signals. We have a signal here that I want to transmit. I can set the strength of the interference signals here. The idea is to adapt the filter coefficients in such a way that they can suppress the interference signals as good as possible. You can play with it already quite well, but I'm still not satisfied with the cost function for the optimization procedure. I think I will bring up something better for it in a future video. What do you think about this idea? Write me in the comments. I hope you have some fun with my videos and Excel tools. I would be really pleased if you were able to take away some insights. Don't forget to download the Excel. The principle can be used universally, and maybe I could wake your interest in this. There is a special hardware and software that can be used to implement really powerful signal processing using digital filters. But that's not my point. I want to explain applications that are on an affordable level and that you can learn from. As always on this channel, I will use the findings myself for an interesting project that is coming soon. Stay tuned. In the upcoming videos I will show how to implement the filter function in C++ code for Arduino boards. Now stay tuned and don't forget to support the channel. See you soon in the coming episodes.